Okay, good afternoon. My name is Bart Cruz. I'm the research director here at the California Air Resources Board, and it's my pleasure to introduce Professor Tony Wexler for today's Chair's Air Quality Seminar. So Tony got his PhD from Caltech in Pasadena in 1990, and then moved to the University of Delaware, where he's a professor of mechanical engineering.
You folks and a lot of other people here too. So the real credit, how it is with being a professor is you never actually do anything, you just have ideas and someone else actually does the work. And so Keith Mine, who's in the audience here, is really the brains behind this first part of the presentation and has done the vast majority of the work here. I just had the interesting idea and then he took it and ran with it wonderfully. And Yang Jing Zhao, who's been with me for many years, makes everything happen in the lab too. He's an instrument genius and just makes things run, keeps things running. And then Ken Pickerton was my co-PI on this work because what we're really presenting for the first talk is actually part one of two parts also. The second part is not the second talk, the second part is the toxicology. So what we're doing here is we're collecting particles from the atmosphere for use in toxicological studies and we're collecting them in a unique way, which I'll describe. And then Kent is in the process of doing the toxicological work, which hopefully he'll be able to report on later in the seminar series. My volume is not up. How's my volume now? I could yell, but not for an hour or two. Okay, how about that? Whoa, that's much more serious. Okay. Great. Okay, so let's move on. So to get going here on this topic, I just want to kind of get people oriented about where we are and how we're going to talk about this. So this is one rendition of what I call the air pollution life cycle. So obviously we start off with the emissions on the left. And there are two classes of emissions, the natural emissions and the anthropogenic emissions. Those emissions then enter the atmosphere and are transported and transformed. So there's mixing with other junk in the atmosphere. There are chemical reactions which transform the compounds from one kind to another. Likewise, phase changes can move things from the particle phase to the gas phase or the gas phase to the particle phase, either through condensation, evaporation, or nucleation. And coagulation can also modify the particle size distribution. So then those particles are transported and then they do something. the two things that are kind of big on the regulatory radar right now are health effects and climate change, because particles and gases play a role in both. Okay, and so then people bitch and moan about the health effects that they're having or whatever, or climate change, and they talk to their politicians about it and fund the Air Resources Board, and regulations appear, and then we get some controls on the emissions. But the controls are obviously only for the in the best of all worlds, they're just for the anthropogenic side. We don't really necessarily cut down all the trees like it's been suggested sometimes. So we just control the anthropogenic emissions. So that's the process here. And so mostly what happens at the Air Resources Board and in the AQMDs around the state and elsewhere is we are working on the regulatory side, trying to take the science and do some rational decision making about what regulations are going to work to with minimum cost reduce the air pollution emissions to bring the air quality, to improve the air quality. Okay, so one question here is all PM created equal, or as George Orwell would say, is some PM created more equal than others? So the sub-question there is, why are we regulating sea spray the same way as we're regulating, say, diesel exhaust? Diesel exhaust is a known carcinogen. Sea spray, people voluntarily go to the beach and breathe sea spray. They don't voluntarily go to the bus depot and, hang around there for a while to kind of inhale that stuff, right? But, the NAAQS is mass-based, so it doesn't discriminate between sea spray, particles in the atmosphere, and diesel exhaust or any other kind of particle in the atmosphere. So we can certainly meet the regulation by continuing to control our emissions, or we hope we can. But maybe we're not doing, maybe that's a little bit of a blunt stick, right? A blunt instrument. Maybe we should be thinking more about which particles in the atmosphere are more or less responsible for the toxicity and try to differentially regulate those ones that are more toxic, and don't spend so much time regulating sea spray, as if we could do that. So how do we deduce the health effects of different kinds of sources? Well, one is epidemiologically, and we have various kinds of evidence out there, all kinds of evidence about that point to various sources. I mean, I work on, some of my other work has to do with lung development in children, and so kids who live near freeways have stunted lung development. This work comes from Southern California, from the excellent people at USC and others. Children growing up where the plume touches down from coal-fired power plants, that also has been shown that those kids have poor lung function, higher incidence of asthma, things like that. And many, many other studies. But these are correlative, not causative. And so the question is there a way to move this to a more toxicological basis? So we asked the same question toxicologically. And a lot of work has been done there, for instance, at Lovelace Respiratory Research Institute, where they take many different sources, vehicles, biomass burning in stoves, and other common sources, generate particles, expose animals to them, and see what kind of health effects they cause. And that's great. That's a wonderful way of doing things. But like every thing we do in this business, there are shortcomings. One of the shortcomings there is you miss the atmospheric processing and the secondary compounds, which may dramatically affect or alter the health effects of the particles that are being emitted. So, we know that in this state, secondary compounds are a huge fraction of the total PM. That is, the secondary compounds are those that are formed by chemical reactions in the atmosphere, not by ones that are directly emitted. That's the primary compounds. So the question is then, could we collect material from the atmosphere that is associated with different sources? Now, the conventional wisdom is that the atmosphere is relatively well mixed. Right? So you go out there with a sampler and you measure over the course of a day or 4 hours or so, and it's a relatively well-mixed situation. Well, what if we look at shorter and shorter time scales? Well, it so happens it's not very well mixed on the shorter time scales. And this is an experience that we have from running a single particle mass spectrometer prior to this work in 4 cities around the country, in Atlanta, Houston, Baltimore, and Pittsburgh, which was part of the EPA supersite program. So the EPA had 8 supersites around the country. These are cities that were monitored very intensively, and people in my group and my collaborators we put single particle mass spectrometers in 4 of those sites and measured in gory detail the particle burden in those cities. And there's 2 things you get out of that. One is you get the chemical composition of the particles one by one, but the other thing you get is you get very high time resolution. So you can see that over short time scales, you don't really have a well-mixed atmosphere. You have a somewhat mixed atmosphere. And so using that as a principle, as a paradigm, let's see if we can run the single particle mass spectrometer in the atmosphere, understand the mixing state of the atmosphere, and then use other co-located instruments to pull apart that mixing state and collect particles that are associated with different sources or combinations of sources. So what's the big idea? Okay, I basically just said it. So you take a single particle mass spectrometer and you put it in the atmosphere, you put it in location. In this case, we put it in Fresno, because we were already doing other experiments there. And you characterize the mixing state of the atmosphere. Now, what does that mean? That means that you are trying to figure out which particle sources affect the site individually and which ones affect the site in combinations that are repeatable. So you run the single particle mass spectrometer for a few weeks, that's what we did, and you characterize that mixing state, which sources come together. So in some cases, you'll have sources that pretty much dominate the site, and I'll show you some of those. In other cases, you may have sources that always come together. So imagine you're at a location and the wind is coming in a particular direction, and if you look in that direction, you see a Burger King, and behind that you see a freeway. Okay, so you're going to always have the freeway and the Burger King particles hitting you at the same time. There's no way to separate those 2 things, right? If you look in a different direction and you see a power plant, and it's not much else going on in that direction, you're going to see mostly power plant emissions when the wind is coming in that direction. Okay, so that's the idea. So then by understanding this mixing state, we can see what kind of common particle sources or combinations of sources are reaching the site at a given time. Then we take 10 ChemVol samplers. ChemVol samplers were developed at Harvard by Petros Koutrakis' group. They're serial impactors, but they're high volume. They run 900 liters per minute, and so you can collect a lot of material. So we obtain 10 of these samplers, and we assign each one to a different situation, to a different source or source combination or other kind of situation that corresponds to a source or a state in the atmosphere. Okay, and we assign them based on what we learned in that 3-week pre-sampling period, right? So that we can then, and hopefully the atmospheric mixing state stays relatively the same over the next 3 weeks, which doesn't always happen, but we lucked out okay this time. And anyway, so then the idea then is that when we assign these things, the single particle mass spectrometer now is going to control which of those high volume samplers is working at a given time. And so when it sees particles of a given composition, it'll turn on the ChemVol and sample with that ChemVol that corresponds to those particles or those source combinations, et cetera, and just keep running that for weeks at a time. Ultimately, you collect enough material that you have enough that you can do toxicological studies. And the important thing is relative toxicity studies. So we can then take PM that we've collected in different size fractions and in these different sources and source combinations and extract PM from those filters and impactor stages and then do toxicological analysis with them. Okay, so now let's get into some of the more, that sort of overview. Let's get into some of the technical meat that happens here. The inlet focuses particles to a beam, a very small, narrow beam that goes into the source region of a mass spectrometer. Okay, in all of these kinds of instruments, there is some kind of energy source which ablates and ionizes the contents of the particles. In our case, it's a high-energy laser. It fires at 50 cycles per second, 50 times per second, about 10 millijoule per pulse, and 193 nanometer wavelength light. So basically in one shot, we ablate and ionize the particle, and then that plasma then is analyzed in a single particle, in a mass spectrometer, time-of-flight mass spectrometer. So the ions fly down the mass spectrometer, we get chemical analysis of the contents of that particle, and then we record that on a computer. So this is an instrument that we ran in all those previous studies I was talking about. This is a RSMS-III, rapid single particle or single-ultrafine-particle mass spectrometer. This is an instrument that we ran in those previous studies, the Atlanta, Houston, Baltimore, and Pittsburgh studies. And it just shows basically how it works. So you've got the, now if I can get the cursor to come up, we're going to be, there it is. So particles come in here, we dry the particles first. They go through a rotary valve where one of, I only show 5 here, but there are actually 9 different lines coming here. Each one goes to a critical orifice which controls the mass flow into this region here. By controlling the mass flow in here, we can change the pressure inside this section. And the pressure in, I lost it, come on back, there we go. And the pressure in this section controls what particle size is focused by this particle focusing element here. And the particle size range that we can focus there is the largest size is something like 1 micron, maybe 1.2 micron. And the lower size, there's no lower limit for the focusing. There's a lower limit for how much analyte we have in the particles. But we can go down to very small particle sizes, in the order of 50 nanometer or so, or even smaller, depending on the composition. So the particles then go through these skimmer stages. The gas is pumped away, and it enters the source region of the mass spectrometer here. The laser is free-fired, and by coincidence, if there's a particle in this region, when the laser fires, then the particle is hit hard. It is ablated and ionized, and the ions are then analyzed in this mass spectrometer. Come back, cursor, there it is. And then we have the microchannel plates on both sides record the signal, amplify it, or they amplify the signal, and it's recorded by a computer. And that's a picture of that same instrument in Pittsburgh, early on in its days in Pittsburgh. So you can see it's a kind of a messy, large instrument, lots of fun to work with, but hard to keep going too, because it's got lots of different parts that can break. And so, just an example of something that from Pittsburgh was, if you then, because we're doing high time resolution measurements with the single particle mass spectrometer, you can correlate those measurements with other things that you're measuring at the same time. So in this case, we can correlate with wind direction. So we can record a particle composition, and for instance, this particular one here, which we had a lot of iron in it, and we surmised was indicative of steel mill. Well, if it really is indicative of a steel mill emission, then we should be able to always see the wind direction coming from the direction of a steel mill. So sure enough, when we correlate the incidence of those particles being recorded and the wind direction, you get the pattern that you're seeing here. And sure enough, if I can get the cursor, there it is, this direction here, there's a steel mill, the USX Corporation steel mill, at 129 degrees, and sure enough, they're emitting particles from their steel manufacturing process, and we see some of those in the atmosphere. So just an example of the kind of thing we can do, because running the same idea with other particle compositions in Pittsburgh, say we get vectors pointing in different directions, and they all point towards different sources in the Pittsburgh area. So that just gives you an example of the kind of thing we can do with it. One particular example that we had was during one day, the wind was just changing direction beautifully, and it brought to the site 3 different coal-fired power plant plumes. The Johns Mansfield plant, the Samius plant, and the dotted blue line there is a Heinz ketchup plant. So when you're buying your Heinz tomato products, they got to boil and cook that stuff, and they do it with coal, right, in Pittsburgh. And so you see that as the wind changed direction, different plumes were brought by the site, and you can beautifully see that here in this diagram. Just let me bring your attention, there's a lot of data here, but let me briefly just bring your attention to a couple of interesting things. If I can get the cursor, there it is. So look at the ozone, right? The ozone is high, and then when the plume hits the site, the first plume hits the site, it goes down, it goes back up again. The second plume hits the site, it goes down, it goes back up again, and then it's it. Now this is titration from NO, right? So you have ozone in the atmosphere, you have NO being emitted by the power plant. The NO titrates the ozone to oxygen, creating NO2, and you can see the ozone drop. And that drop corresponds to increases in other things, like for instance here's the SO2, right? So SO2 goes up when the ozone goes down because that's when the plume hits. Likewise here, this is the SO2 is going up when the ozone goes down. So that's just classic Classic stuff. Okay, so I just wanted to say all those things to demonstrate the kind of power that the single particle instrument gives you in analyzing what's going on in the atmosphere. So now we're going to use that power to do this source-oriented sampling, is what I call it. So, so here's the general schematic for how things are going to go. So we're going to have a stack. We're going to draw particles into these 10 ChemVol samplers. First, we're going to get rid of the coarser particles. We're going to go through a manifold, and there are going to be 10 of these samplers coming off the manifold. Another manifold then to a pump. And I'll show you all these things. And here is the mass spectrometer, the single particle mass spectrometer. And it's going to look and see what's going on in the atmosphere, look and see what the mixing state is in the atmosphere, and then control, come back cursor, and control one of these valves to turn it on when the composition corresponds to what we've pre-assigned to each of the different ChemVols. And this is a schematic diagram that Keith drew up for how everything is positioned inside our trailer. We have a trailer portable laboratory that we use to schlep all this junk around. In the laboratory, as you'll see, and you'll see a picture coming up soon if I get the cursor back. On the right-hand side, you'll see the single particle mass spectrometer. On the left-hand side, you'll see the bank of ChemVols. There's two different stacks. You won't see everything that's on the outside, but anyway, air comes in here. We take off the coarse sample, and then the fine samples are collected here. And another stack where we bring in air that goes to the single particle mass spec, and you can see the stacks are roughly the same height and not very far from each other. So they're basically getting the same air. Okay, and that's a picture of the mass spectrometer that we used in Fresno for this work. It's a little different than the one I showed you earlier, but it does basically the same job. You can see so here's the dryer I talked about. The air comes in here and is dried. It goes, here's the valve that controls the mass flow rate into this section here, and then you can't really see it, but then there's a focusing element behind all this, which focuses the particles into the source region of the mass spectrometer, which is there. And this purple guy down here is the laser. It fires, the light comes up through lenses and or in openings in here, and in this section here is where the particles are ablated and ionized, and then ions fly down this tube and are recorded here by this computer. Okay. The other part of this instrument are the ChemVol sampling. So here's the stack. You saw the diagram before. Here's the actual stack, and actually there is the other stack that goes for the single particle mass spec on the telephone pole. And so here's the one for the large volume sampling duct here. The air comes down, goes through a coarse cut stage here. Inside, it comes inside right over there, and then comes into these two manifolds, and below them are 5 different ChemVols for each manifold. And there are valves shown below here, which then control which ones are on and off. This is the manifold that brings air out the bottom. It goes through a flow meter here, and is pumped into this pump and then exhausted at ground level through this muffler. And this is a VFD, variable frequency drive controller. One of the shortcomings we had at the site was that only 2-phase power was available, and the pump is 3-phase because it's pumping a lot of air against a large pressure drop. But that actually worked out very well for us because these VFD controllers are whatever, they're my favorite thing these days. They not only convert 2-phase or single-phase power to 3-phase power, but they also have a PID controller inside them, so we can take the output from the flow meter, run that into the VFD, and make sure that the flow rate stayed constant in each of these different samplers. And that was important because as the samplers get loaded up, as the filter gets loaded up, the resistance goes up. And so you have to keep increasing the power to the pump to keep the volume flow rate the same. So we accomplish that way. And if you want to see this kind of more 3D, then you can go to photosynth.net and search for my name, Wexler, and you will see Photosynth is a cool website. You have to have a PC because it's a Microsoft product. Does not work on a Mac. How's that? That's how it goes, right? But if you do have access to a PC, you can go in there and kind of like look around inside the trailer. It's kind of slick. Okay, so now the hard part is the algorithm. So it's all very nice to say, well, we're going to look and see what particles are in the atmosphere, and when we see the particles that are there, we're going to turn on the right ChemVol to sample that stuff. But the reality is much more difficult than that. And so I'm going to pain you with going through the algorithm, because I think I know many of you may glaze over, and I apologize for that. Take a little nap right now if that's necessary. But for some of you, you're going to appreciate this a very interesting thing that we have to do in order to get this all to work properly. And again, I credit Keith with putting a tremendous amount of time and intellectual muscle power into making all this happen. Okay, so there are two different stages here. There's the pre-study where we run the instrument for a few weeks to characterize the mixing state of the atmosphere, and then there's the collection step where we then, once we know the mixing state, we assign different particles or different particles or particle combinations to different chemvols, and then we run and we collect. Okay, so for the first stage, this pre-study, we don't run the chemvols at all. We're just trying to characterize the mixing state. Okay, so let me take you through it. If you're not napping. So first of all, we have the single particle mass spectrometer, and we acquired the single particle mass spectra. And first of all, we calibrate them. We normalize them, make Euclidean norms, so that the sum of the squares of the peaks in the mass spectrum are 1. Okay, then we run it through come on, cursor baby, where are you? There you are. We run it through a clustering algorithm, which then looks to see which particle spectra look like other particle spectra, because not all particles are created equal. But you can see that ones that come from the same source have very similar mass spectra. Okay, so we're going to look at which ones are similar using the clustering algorithm, and then if we get enough particles that are similar, we're going to enter that into a library, which we're then going to use in a moment. And sometimes, though, we need to do this manually because we need to look at them and say, okay, there are particles that look different, but they actually have similarities. We may put them together in the same cluster and do other things that only an intelligent human being would be able to come up with. Maybe that's an exaggeration for our smartness, but anyway. Okay, cursor, here we are. Okay, so now we're going to try to partition the mass spectra among different particle classes. And more important than that, we're going to need to look at, we've collected all these particle spectra. We're going to need to look at the chronological sequence of when they occurred during that 3-week pre-study period, because we want to know which ones are coming together, right? So just the fact that we get, say, a bunch of particles from a steel mill doesn't mean that they're not coming along with some other particles like the Burger King or whatever that happens to be in the same place. We need to figure out not only which kinds of particles that are each indicative of different sources, which ones are coming together, but which ones are coming with other sources at the same time, because that's the only way we're going to be able to collect with the chemvol. And be able to separate things in time so that we have different time periods where the source is dominated by a particular source or a combination of sources that we can then collect separately. Okay, so now we're going to make what I'm apologize for all the different terms, but we've struggled with how to communicate this without using some terminology. So we cluster these particles into classes of particles, particle classes here, and then we cluster the classes into class combinations. Okay, and the class combinations are particles that come together with each other, that are different composition but come together with each other, like, say, would be indicative of, say, a Burger King with a freeway behind it, where you would get two different kinds of particles at the same time. Okay? So, this thing's really hard. Okay, good. And so we have we develop class combinations, and then by clustering the particle classes together using the time that they appear, and then, and also do a manual clustering to come up with basically how we're going to assign the different particle composition classes and class combinations to different chemvol samplers. That is, when they appear at the same time in combinations or individually, then we're going to use that to sample. I hope that got across. Okay, so now we've done our pre-study, and we have assigned to each of the different chemvols a task to collect a certain combination of particles or something else, which we'll get to. But yeah, they're all assigned. Okay, so now we're going to run for a few weeks, and with the idea is to collect enough mass to do the toxicological studies. Okay, so we run the single particle mass spectrometer. It turns out we have these digitizers, and we combine the data with two different D to A to D converters. And whoa, come on, baby, where's this cursor? Okay. And the first thing is, do we get a particle hit? Because sometimes we miss the particles. Actually, usually we miss particles, but hit them often enough. We combine the high and low signals together into a new spectrum. We do the time to mass calibration. And again, this is something that has to happen all automatically. That is, we're collecting in a mass spectrometer, time-of-flight mass spectrometer, you're collecting the particles on the time that they arrive at the detector, and you have to convert that into the mass of the ion. Okay, so there's a little bit of a nonlinear conversion that goes on there. You correct for noise, you bin all the masses into unit mass bins, and then you are going to look at when a spectrum and a cluster look similar. Okay, so this is a dot product here. When you dot product two vectors together that have been normalized, that have been Euclidean normalized, if the two vectors are exactly the same, you get a 1. Okay, the answer is 1. If the two vectors are different, then you start getting numbers that are lower than 1. If they're totally orthogonal to each other, that is perpendicular to each other, then you get 0. Okay? And so we're looking for when particles that we are looking at are similar to particles that are in the cluster, the class combinations that we've already pre-assigned. Okay, so are they one of the classes that we already have? If they're not, then we want to save that because maybe there's going to be some new source that appeared since our pre-study. So we want to hold on to that and remember that for adjustment later. Okay, if it is something we've already seen in our library of particle classes, then we're going to be looking for how much time we have because we want to make sure we've got enough hits and enough time elapsed so we get good statistics. And then we're going to try to construct a class combination. So now what we're going to do is we're going to get lots of particle hits, and we're going to look at the relative weight of those very many particle hits to see if that corresponds to what we have in our class combination library. Come on, cursor. Come on, cursor. There we go. Okay, so we're going to look now in the class combination. We're going to develop a class combination vector. We're going to see whether that has a dot product that's high enough to say, okay, we can assign it to one of the chemvols. Okay, if it's true, okay, let's sample on that chemvol. If it's false, again, we're going to save that class combination in a library because maybe it's a new class combination that we hadn't seen in the pre-study. We want to be able to come back and deal with that. Okay, and then once we know which class combination we're working with, we know which chemvol we should be sampling with, and then we have various converters, various equipment then to turn on the different chemvol that corresponds to it, and then we're sampling off that chemvol. Okay, and so this is happening all the time, very continuously. It's always looking at the particles in the atmosphere, classifying them, and then adjusting which chemvol to be turning on or off continuously with time scale in the order of minutes, basically, to get good time resolution. And I'll talk a little bit about sort of the boundary conditions for those time periods in a moment. Okay, so just I'm going to give you a couple of the source combinations. There was lots of different data, tremendous amount of data we gathered, and there's not enough time or probably coffee in your veins to put up with all of the stuff that we've collected, but we will. I'll just deal with a couple of things. So one of them is that in Fresno, as it's no surprise, wood burning, biomass burning is a big source of particles there. And so one of the indicators for biomass burning is potassium in the particles. And so when we hit these particles with our laser, you get a bunch of compounds coming out of there, which are indicative of the composition of the particle and its source, and one of them is potassium. And so you can see here, this is a source combination where we have identified here 42 different kinds of typical particles in Fresno. During some time periods, you see that these particles, all but the first one there, have a very, very low probability, a low incidence, but that one potassium one has a very high incidence. And so that's one where you just have, those are time periods where particle composition is predominantly from biomass burning. And so we can say, okay, that's one of the chemvols. Okay, another chemvol, it's hard to find incidences where you don't see any potassium because biomass burning is so prevalent in Fresno, but you certainly see time periods where there's mixtures of lots of other interesting things in there. So here are particles, so during this kind of time period, for this chemvol assigned to this source combination 2, certainly you see the pure potassium particles from wood burning, But you also see, say, potassium particles that are coated with ammonium nitrate. Okay, so those are particles that were probably emitted further away and then had more atmospheric processing before they reached the site, and so they had ammonium nitrate condensed on them. Or you see particles that are potassium, again indicative of biomass burning, but with also an EC and OC component, so or elemental carbon and organic carbon components and the ammonium nitrate on there, or the EC and OC without the potassium. So again, these are typically more aged particles. And lots of other things. So you're seeing that we're collecting particles that are indicative of sources, but also indicative of secondary processing of material condensed on the particles, because one of the open questions here is how much of the toxicity is from the primary emission, how much of the toxicity is secondary material formed in the atmosphere that may be on all the particles that are there, or all the particles that have been there long enough to have that condensation. Okay, now lots of numbers. So just to give you a feeling, maybe it's better to just look in your notes or look back at the slide presentation later, but there's lots of numbers here having to do with how we ran. We ran two different time periods, one in the summer of 8 and the other in the winter of 9. We chose to focus on two different particle size during these different time periods. We did a lot of, this is our first 2 experiments, and so we're learning a lot as we do these things. We chose 70 nanometer particles for our summer experiment and 150 nanometers for our winter experiment. We used this dot product threshold to understand whether particles were in the same particle class. That is, as I said, if the dot product is 1, they're identical. If it's 0, they're totally perpendicular to each other. So we chose, if they're higher than 0.8, we're going to call those particles similar to each other. And if it's below 0.8, we're going to say they're dissimilar from each other. Okay, cursor, let's go. So, and so there's a number of different characteristics here and parameters that we have in the system. So, for instance, maximum time between successive particle observations. We want to, if things are going slowly, we don't want to wait forever for the next particle hit. And things are going slowly when the concentration of particles in the atmosphere is very low. And so we have thresholds there. Lots of different numbers here. Another, coming back to this classification, this dot product class, come on, there it is that we also need a threshold for when the class combinations are similar. So that is when we see not only that the spectra are similar, but that the relative weight or the relative amount of different particles are similar to each other. And so again, we have to do another classification based on the dot product. And so we use different thresholds for the summer and the winter. Oops. Et cetera, et cetera. Okay, maybe that's enough. One of the things I want to talk about is this last one here. So one thing that we learned in the summer that was very interesting had to do with boundary conditions. And so what happens is, as you're sampling, the air is changing. And so the question comes up is, when do you switch to a different chemvol? So as long as the particles are coming along that you're seeing with your mass spectrometer are sort of the same as you have seen, okay, you stick with that chemvol. But then things start changing, but you don't know when they're changing until it's sort of too late, right? So what we do in the algorithm is if we see things starting to change, then we had different algorithms that we used for the summer and the winter. In the summer, when things started changing, we would turn off, we would wait, and then once we saw enough evidence, we would switch to the new one. Okay? In the winter, we actually did some calculations that showed that it's better to actually wait a longer period of time, to wait just to make sure you got the new stuff. And that ended up improving our statistics and decreasing contamination from other particle classes into our sampling, if any of that is comprehensible to anybody. Okay, so then some metadata about what we actually sampled in Fresno. Again, there's the summer and the winter experiments, and for each of those there's a pre-study and then the chemvol sampling part of the study, and there you have the dates, and you have the number of hours that we sampled, and the number of mass spectra that we recorded during that time. You can see you get a tremendous amount of data over a relatively short period. And we ended up classifying things very differently between the summer and the winters, just because we learned, for two reasons. One is we learned how to do things better from the summer experiment to the winter one, and also because just the mix of stuff in the atmosphere is different in the summer and the winter. And and so then we had a lot of these. So then again, we get a bunch of mass spectra Come on, cursor. And then we classify them into these class combinations, and this is the different class combination vectors that we were able to build during that time, each of those then corresponding to a choice between sticking with the current chem-vol or switching to a new one. And here's another interesting way of looking at this, which this is for the summer. I think it's for the summer experiment. No, I think it's for the summer experiment. This is a map of the incidence of the different class combinations. Okay, so here's a source combination number here, and this is just the time period across here, and we put a dot wherever we would have that one on. Okay, and what you can see is some interesting things here. One is that, of course, that some of these class combinations appear more often than others, right? And we just ordered them basically in order of prevalence. So sometimes you see things very often, like the biomass burning potassium signal, and sometimes you see things very infrequently. They're just class combinations that you just don't see coming along very often. You also see diurnal patterns in here. You see some things like this one, occur more at night, and this one here occur more in the daytime. It's exactly what you would expect, because there are different sources that are operating more or less different times of the day. And so you would expect us to have different things that are happening in some kind of diurnal cycle as people go about their life, commuting and turning on their heater for their house or barbecuing at home or whatever it might be. Okay, so more data. I'm kind of getting tired of presenting lots of data, but I do have it here, so I should go over it a little bit. So this is for the summer experiment, the first chem-vol, and you can see this is the number of hours that we sampled. So these are in order of prevalence, and so they also end up being in order of how much we were able to collect in terms of mass. Except the bottom ones here are kind of miscellaneous, which I'll get to in a moment. So, so here is the amount of time that we sampled. Here's the number of hits that we obtained, and the total number of sampling intervals that happened during those times. And you can see we thought we had them ordered in order of prevalence, but then sometimes you get some surprises, and you see more of something that wasn't that way in the pre-sampling. And then here is our estimate of how much mass we collected. Now, our goal was to collect 1 milligram of material, because that's what the toxicologists said they needed in order to do their part of the work. And so you can see for the source combinations that are most prevalent, come on cursor, where are you? Yep. There we are. That we collected quite a bit more than 1 milligram. Some of them somewhat less than 1 milligram. We just weren't as successful because the ultrafine particles don't carry a lot of mass, and we just didn't see these combinations, these source combinations, very, very frequently. But then you see other ones where we collect plenty of material. Okay, so these ones down here, 9 and 10. 10 is the we don't know what's going on chem-vol. Okay, that happens frequently. We have source combinations we didn't anticipate, or combinations that just didn't rise to the top in our ordering of prevalence. And there's lots of those things. And so we ran that chem-vol 10 when we didn't have a clear idea of what was going on in the atmosphere at that time. And so clearly, you can see that most of the time we don't know what's going on. That's sort of typical of scientists, I guess. Chem-vol 9 was basically in the middle of the day. And what happened there was that we observed during our pre-study that when the boundary layer lifts, the concentration of particles goes down tremendously, as you'd expect. And so that it's much harder then to get a high enough hit rate with the mass spectrometer to be able to characterize what's going on. And so we just then said, okay, during the daytime, we're going to collect all of our particles in 9 and not run the mass spectrometer. And during other times when the boundary layer is lower, we have a higher hit rate, then we're going to run the algorithm which I described to you before. Okay, and this is, again, you have this in the slide and in notes for those of you who came to the room. The same kind of information for the winter study. Okay. Now, how did we do? So here are particle class distributions. So you can see we have different particle classes here, and we haven't divided these into the particle class combinations yet. This is just the particle classes. So elemental carbon, potassium. This is a carbonaceous particle with ammonium nitrate coated on it. This is an ECOC particle, elemental carbon and organic carbon mixed. Here's a sodium-potassium particle, kind of particle. Here's a potassium with carbon peaks with it. Here's one of the metal particles, other metal particles here, 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 right? And let's see. Oh, yes, and then the amines. Amines, although this kind of instrument is not really good at analyzing most organic compounds, it happens to be very good at analyzing amines. And as we know from other studies, amines are prevalent in the San Joaquin Valley, mostly due to concentrated animal feeding operations and other heavy emitters of amines. So here is another way of looking at things for the winter. Here is a mixed metal, a carbon particle, kind of carbonaceous kind of particle. Here's again the carbonaceous ammonium nitrate, elemental carbon particle, a metal, carbon, and ammonium nitrate particle, another miscellaneous metal particle here without the other stuff in it, and a particle that's pretty much purely carbon. So these are just to give you a feeling for the different kinds of particles that we see and how we classify them into their major kind of categories. We get many, many more particles, and you could classify them in many, many more fine classifications, but at some point it doesn't become useful anymore. So we try to combine the particles into things that look similar to each other. Okay. Now, now the question is, were we able to collect things during the actual sampling period, like during this, like the pre-study? And so here are how we assigned source combinations, class combinations, to the different chem-vols for the summer and winter, and the prevalence that were collected in the red versus what we had anticipated in the gray, okay, from the pre-study. And so you can see that we did very well in some and not very well in others. So for instance, this chem-vol 1, the size of the red bars is nearly identical to the size of the gray bars, and so we actually collected pretty much what we intended to collect. Chem-vol 2 also quite similar. But now chem-vol 3, you see, we missed it. You know, it's just that by probability, we just weren't able to capture exactly what we were trying to capture. And chem-vol 4, more similar, not as good as these two, not as bad as this one, intermediate. And you can see the same kind of thing happening with the other classes. Quite good here, quite good. In the winter, we did much better. You can see quite good. And that's probably just because we learned better how to do this. Okay, now, another way of looking at this is looking at what we collected versus what we tried to collect. And if the dot product of those two things is close to 1, we did very well. And so we're comparing what we collected to what we tried to collect, but also, since the ones on the diagonal are those, and if those are 1, we did perfectly well on the collection. We also want to make sure that we did poorly when we should do poorly. Okay, so those are the off-diagonal ones, right? So ideally, these matrices here would be 1 along the diagonal and 0 off-diagonal. But because the class combinations that we observed in Fresno aren't perpendicular to each other in composition space, you can't get that, okay? And so, but we did quite well. So for instance, you can see that as far as the mass spectra are concerned, we anticipated, we got 90% or better. As far as the chem-vol assignments are concerned, we did pretty well. Here's a 73. That's a little bit lower than 78, but otherwise we're getting up to the high 80s or so, mid-high 80s. And the other important thing is that the off-diagonals, although not 0, are much smaller than the on-diagonals. Not always the case, but often the case. So here, for instance, is a 72. That's pretty high. It gets comparable to some of the on-diagonals, but we see most of them are actually quite a bit lower. And there's no way to get, or not that I understand anyway, no way to get a perfect separation of 1s in the diagonal and 0s off diagonal, because the stuff in the atmosphere is not independent of each other. Different kinds of particles that you get, or maybe I should say parcels of air containing particles, aren't always different from each other. There's going to be overlap because of mixing between them, and because of secondary compounds that end up on everything. Here's the same thing for the winter. Now again, we were more experienced in the winter, and so we improved our algorithm, and look at that. We got much, much higher values along the diagonal. See those there? And correspondingly, actually quite similar values, maybe a little bit lower on the off-diagonal, but the important thing is that the on-diagonals were quite high. And so we're doing pretty well, collecting what we intended to collect. Okay. Now another difficult concept here is what I call boundary conditions. And so That comes back to something I talked about earlier of you're sitting there with your single particle mass spectrometer, you're collecting particles, or you're in recording their composition, and now things start changing, and what do you do? All right? When do you switch to another ChemVol or turn it off or put it in the I don't know what's going on ChemVol or something? So here are statistics about, okay, and so ideally what you'd like is that you're collecting for a long period of time. Because if every time, let's just, for discussion purposes, let's say our time chunk is 5 minutes. We're going to collect for 5 minutes. We're going to look and switch or not switch every 5 minutes. Okay? If every time we collected it was for only 5 minutes, then you'd have a lot of boundary contamination. Because as the composition is shifting, you're not instantaneously switching to a different ChemVol. Okay? So you're going to have contamination into that ChemVol from where it should be, because you don't have instantaneous information to make the switch. So the question then is, how often do we get single time period chunks in our collection, and how many 2, and how many 3, and how many 4? And you really like to have many of them be multiples, because then what happens at the boundaries have less of an effect on what you've collected. So you can see that for some of these you have, and so this is a cumulative graph of single, double, triples, et cetera, up into the 20s of particles. Not of particles, but of time chunks, where you're successively getting the same composition, or the same class combination. And so you can see that for some of these, like ChemVol-III, actually we didn't do very well. It's not really our fault, it's the atmosphere's fault, where really, you don't really get many more than 3 or 4 at a time, successive time chunks when you're collecting. Whereas for some of them, like this ChemVol-I, you're getting lots of time periods where there are many of these, say, 5-minute time chunks where you're collecting material. So you have you have less boundary contamination. Okay? I hope that got across to some people who are listening in. That's it. So I want to thank Keith for a tremendous effort here. I mean, just all instrumentation and algorithm development and some real serious thinking and discussions together about how to pull this thing off. And Yang Jing for really making everything run in the field when we didn't know what was going on with broken instruments and this and that. And you guys for mostly staying awake. Yeah, thanks, Ralph, for waking up for that. And the ARB and the Electric Power Research Institute for financial support and moral support, too, because this was a very risky project. A lot of new stuff here. And so I appreciate everybody hanging with us as we delved into this brand new field. Thanks a lot, and I'll take questions. Yeah.
One moment.
Microphone.
I'm sitting here young and naive, and I'm just trying to wrap my mind around
Young and naive.
You're measuring single particles at a time, and that there's so many particles in the atmosphere. And at what point, you mentioned time intervals. Is there a set number of particles you have to measure before you can identify a...
Yeah, we need to, yeah, and there was all in those tables there. But yeah, okay, so what we're doing is these class combination vectors are, I mean, let me come back to that example of the Burger King with the freeway behind it. Let's say that during our pre-study, we, the relative weight of those two sources was, let's say, 5 to 3. 5 Burger King particles to 3 freeway particles, okay? So we would need to see at least 8 particles then on, to get that ratio, okay? But actually you need to see more than that because you need to get good statistics to see whether we're close. Now we're not asking to see exactly 5 and exactly 3. We're asking to see something like 5 and 3, not 3 and 5 for sure, something like 5 and 3 to say, okay, that's the class combination that belongs in this ChemVol. And so, we need to see tens of particles or so before we know what we're doing. But it depends on it really depends on the class combination, because for like the potassium particle, if you're just seeing a lot of that, then life's easier because it's just a single kind of particle in that class. And for classes that are more complicated, you need to get more statistics before you know what's going on.
That's all in the algorithm.
Yeah, well, as best as we can do. Yeah.
Is there, can you hear me?
It's on, yep.
Is there like an ideal location you could think of in California, either in terms of the meteorology and the sources for applying this technique, or stuff that talks people want to look at a particular location?
Yeah,
You
good
mentioned that Fresno is where you guys were set up, but
Right.
is there like an ideal place?
Well, I think Fresno is probably one of the least ideal places. No fault of Fresno's, but prevailing winds would be very helpful. And Fresno's not known for its prevailing winds. The air kind of just sort of moseys around down there. So a place with prevailing winds would be much easier for us to work with. So the Bay Area, LA basin, where you have clear diurnal cycles of winds up, inland and then back out again during the diurnal cycle. So yeah, places where there's more prevailing winds is certainly going to be easier for us to work with, because then you're going to get clear directions, and those wind directions will help us bring clear, distinct sources and source combinations to the site.
Hi, Tony. Very nice presentation. Thank you. Especially in San Joaquin Valley, and this might be a good follow-up question to the one that was just asked. You have so many types of particles that are almost valley-wide, like the ammonium nitrate or even the wood burning and whatnot.
Yep.
So if you had some kind of stagnation period, for example, in the winter, and you just constantly have lots of potassium and lots of ammonium nitrate, how would you decide on which high vol to use at different
Chem vol,
times?
yeah.
Chem vol.
Yeah, so it just, in our experience for those time periods, okay, so there's a few things here. One is we didn't see that kind. We didn't see this like everything looking the same very much, okay? And I think that's partly because of the single particle mass spec, and because it's looking at, if when you're mixing lots of particles together onto a filter or impactor substrate, you might come to that conclusion that the particles all look like ammonium nitrate or whatever. But if you look at the particles one by one, they all have seeds in them. The ammonium nitrate and the secondary organics, they're condensing on something. And that something often has some kind of indication of where it came from, some metals or whatever, that can tell us what the primary source was. And so those metals don't make up a large fraction of the mass of the particle, and so may not appear when you do a mass analysis, but they certainly appear in the mass spectrum. We can certainly just differentiate them from other things that are there. So yeah, I hope that answers your question.
Well, so in one chem vol, you would have, let's say, a Burger King signal that arrived on either a different background particles, if you will.
Yes, right. So and we don't classify them as Burger King. That's my example. But for instance, if you see a carbonaceous particle, or you see a carbonaceous particle without ammonium nitrate, you could conclude, and we have to do more work on this to figure out exactly what happened there. But you conclude that okay, then maybe the carbonaceous particle was a particle emitted by a vehicle going down Shaw Avenue, which is where we were in Fresno. Or maybe another carbonaceous particle with ammonium nitrate on it was one that was emitted further away. The ammonium nitrate condensed on that, and then we detected it with the mass spectrometer. So you get a feeling for the different amounts of secondary processing that happens. So I don't know if I'm exactly answering your question, but I hope I'm getting close anyway.
Yeah, you mentioned earlier that you got a better correlation in the winter than in the summer. Because you were better practiced, you thought?
Yes.
In terms of, I guess, between the training period and the longer sampling period. But then thinking about the prevailing winds, as you just spoke about, between winter and summer, you have got a little more prevailing wind pattern type thing in the winter. In the summer, it's probably more constant winds. You don't get changes in the weather you do in the winter. Is it possible that that's a factor, or is it some other factors that could lead to the better correlation in the winter?
Yeah, I don't know. I don't know. Do you, Keith, you have any feeling for that?
Hard to say. Probably a mixture of both, using higher thresholds for the clustering. We haven't really gone back and done any of the meteorological stuff yet, but it definitely could be.
Okay, thanks. Hi, could you just comment on how the particles are, I guess, isolated and processed before the tox studies?
So okay, so the ChemVol sampler, I didn't go over that in gory detail, apologize. So we actually ran the ChemVol sampler in the summer and the winter in different ways, the ChemVol samplers. Again, because we learned as we were going. So in the summertime, we have an after filter to collect the particles that are between 0 and 170 nanometer. Then the impactor stage ahead of that collects particles from 170 nanometers to 1 micron. And then we had common impactors before that to collect material that was larger than 1 micron. The useful samples were the same for the winter, except that we put 1 micron impactor stages on all of them instead of having one before the manifold, because for a few reasons. One is that the loading got to be high, and we didn't want bounce from that stage into the lower stages. And the other reason was I was just a little bit paranoid about even particles from the ducting getting into the samples, and so I wanted to have a cut right before each of the ChemVols. Is that what you want? Oh, then okay. Then we have to then extract the material. Is that what you're interested in?
Yeah.
Yeah. Okay. So then Keith spent a lot of time working on the extraction methods. It seems that extracting particles from filters and impactor stages is kind of an art, not a science. There are lots of protocols out there people have developed for how to do it, but the efficiency, the amount of material you get, varies tremendously from group to group. And that may be partly due to the substrate and partly due to the composition of particles in the atmosphere. But because this is highly valuable material that we collected here, and we needed to have enough for the toxicological studies, Keith spent a lot of time working on techniques for getting material off the filters and making sure we weren't getting filter material in the process. So it's basically a sonication method with water.
Oh.
Yeah.
Yeah, I'm not sure if this is you or Keith who needs to address this, but it's inherent in clustering that you can, by adjusting the number of clusters you select, you can get very different results in your clustering. Did you use a particular criterion for selecting the final set of clusters?
Yes, we did. So you may remember in the flow diagram there was the expert opinion part. And that's, that's reality here, in that you need to do, so there's a few criteria for selecting the clustering. First of all, they really do have to have dot products that are high. Otherwise, let's not even bother with it. But if you have, how do I say this? If you have a bunch of dot products that are high, but they're different than each other, you're not going to get more than 1 milligram, right? Because you're just not, unless you sample for a year or something, right? So what we did was we would say, okay, let's just take all of the metal particles and put them into one cluster combination. So, because that will just tell us then about the relative toxicity of those heavily metal particles versus the other stuff that we see. And so we had to, there was a kind of expert opinion, about, okay, well, our goal here is toxicity. We can always look at the mass spectra and learn all kinds of things about what's happening in the atmosphere. But where our goal is to collect enough material to do the toxicity studies. So we had to put things together that seemed logical, like heavily metal particles, and separate those from, say, the ammonium nitrate particles or the potassium-dominated biomass particles and things like that. And so we use the algorithm to cluster them to a finite number, tens of them, and then we looked at them and said, okay, what's reasonable here? How do we want to actually collect for the toxicity studies? William in the front here.
You could go out and collect particles from the different sources. So,
yes, it's on.
And so what you're mainly interested in is some possibly aging effects from different sources.
Exactly.
And so what types of markers did you use to separate out different types of aging?
So the different types of aging is, for instance, the ammonium nitrate. So that's a strictly secondary material. And so we have particles which maybe you saw, or I could go back and show you, but there were classes of particles that had a very small amount of ammonium nitrate on them, and classes of particles that had a lot of ammonium nitrate on them, indicating more or less secondary composition. And that same thing is also, although not as certain, but the organic carbon is also possibly a similar indicator. You see particles that are more elemental carbon and particles that are more organic carbon. And we don't really know how much of that organic carbon is secondary or primary, but certainly more of it would indicate generally more secondary, but not as definitive as the ammonium nitrate. Yeah.
Yeah, apparently we don't have any questions on the web, so I guess they all fell asleep there.
Good. I did my job.
Yeah. I guess we'd like to thank Tony for a very good presentation. At least kept us awake here and had some good questions. So, we really look forward to the talks work that's going to follow, and I'm glad that you've been spending the time on figuring out how best to give those samples to Kent Pinkerton. And we certainly look forward to those results, and interesting to see how the toxicology, how the toxicity varies for these different sample types that Tony and Keith have collected in Fresno, and that should be very useful for us. So at this point, after we thank Tony, we should take a 5-minute break and let him do whatever he needs to.
This is where we have a word from our sponsor. That was the word from our sponsor.
Right. we didn't start out saying that the restrooms are out that way to the left, but hopefully some of you can be back here in 5 minutes, and we'll go on with the seminar on the improved vases that William managed, and he'll introduce that topic for us in a little bit. So see you in a few minutes.
It's from a air district.
Oh, that's the air district there.
Yeah, I think it's probably important.
You mentioned him.
Yeah, but I think it's important.
Very helpful.
Yeah, but I think it's good that we answer.
Yeah, sure.
So I'll leave a copy for Tony. So you want to take that as a cue when we start off? Okay. Well, yeah, yeah, they both have
Tony,
copies. So.
Right, yeah. I don't.
Well, you take it over, Ralph.
Okay.
Oh, Tony can too, but it wouldn't be mad if you made a comment.
Yeah, yeah.
Yeah, we should start it right now. Right now, yeah. Start.
Okay, we're back from our break. This is Ralph Proper, for those on the web. We, in fact, did get at the last minute a question from the web on the talk that we've just had. So I'll pass this over to Tony, and he can deal with the question from David